Hello and welcome back to the lecture of time series econometrics. So in the past few lectures, we have been dealing with the different mathematical properties of higher order AR and MA series. And in this lecture, we're actually going to do a problem where we'll use some of the concepts that we have developed so far. So the problem is like that. We have a AR2 equation as follows: yt equal to one third of yt minus 1 plus half of yt minus 2 and epsilon t. Now, we need to identify if the process is stationary. And second, we need to estimate the mean. And third is we need to estimate the value of row 1 and row 2. So we will see how the things that we have learned so far is going to be useful here. So the first part is whether the process is stationary or not. To check that, you remember we used the lag operator and we used the AR characteristics polynomial, and then we got the AR characteristics equation. We equated that with 0. We found out the roots, and then we actually inverted that root to sort of ensure that the invertibility property is holding true, because we need to ensure that the series is stationary, and for that we need to invert them, and then we identified the value of the expression of the roots of the equation, and which should be less than 1, right? So when we do for the first time, when we do not invert, our roots are outside the unit circle in a complex plane. So in that case, I have to have my roots more than 1. And when I invert them, they have to be less than 1, because I'm inverting the roots, right? So this is the basic theory that you need to remember when we are trying to identify if the process is stationary or not. So let us go step by step for that. So first we will actually use a lag operator, okay? And then we will use the AR characteristics polynomial and then AR characteristics equation. Then we'll invert the roots, and then finally we'll check the stationarity condition, right? So that's basically the strategy. So let's actually do that. So my equation here is very simple. Yt is equal to, so one third, I think, yeah, one third yt minus 1 half yt minus 2 plus epsilon t. All right. Now, as I said, that we are going to first use the lag operator. Okay, so that means I'm going to say one third L yt. We are actually going to do the whole process. Okay, half L square yt and my epsilon t. Right? Now I take the yt, all the yt terms on the left hand side, and take yt common. Yt is equal to 1 minus L by 3 minus L square by 2 is equal to ET, right? And then we actually said that this value 1 minus L by 3 minus L square by 2 is nothing but 0. Now to get basically the roots, I don't really use a lag operator, so I use a variable. Let's say a variable which has similar properties, but it's a variable. Okay, so I 1 minus x by 3 minus x square by 2 is equal to 0, right? So this is my AR characteristics equation. AR characteristics equation. Okay. So let's write down some phi x, for example. Now the next step is we need to invert the roots, right? So from here, if I get the roots, I will try to identify if the roots are greater than 1, but I will invert them and I will make sure that the roots are less than 1, right? So that's the strategy. So for inversion of the roots, what I do is, so let's write down the name of the equation. So number, let's put some numbers to the equation, 1, 2. So when I invert, I actually say, let's use equation 1. Let's use a different color for the next step. Okay. So what I do is I actually take L square common, because I am trying to invert the roots, and I have L to the power minus 2 minus L to the power minus 1 by 3 minus half is equal to 0, right? Now I can actually, I want to replace this lambda equal to L to the power minus 1, right? So if I do that, so my equation will be lambda square minus lambda by 3 minus half is equal to 0. So that's what I get after inversion. Now I need to get the roots, and I need to just equate them with my condition that the roots need to be less than 1. So let us find out the roots. Let's again use a different color. Roots are going to be, let's see, roots are going to be minus b is 1/3 plus minus b square is 1 by 9. 4ac is 4 by 2, and I have my 2a. 2a is 2, right? A is 1, which means here I have 1/3 plus minus, I have, if I take say 1 by 9 plus 2 is 19, actually 19 by 9 by 2, right? So which means actually 1 plus minus root 19 by 6, right? So these are the values of the root, and if you see the values of the root, so 1 plus root 19 by 6 is basically less than 6, and 1 minus root 19 by 6, if you divide by 6, is again going to be less than 1. So both the roots are basically less than 1. So both are less than 1, right? So that is to say that my conditions are satisfied for AR2 series to be stationary. So I can write, so this AR2 series is stationary. Okay, this the AR2 series is stationary. So my first problem is solved. Okay, next I will try to get the mean. The second problem is I need to identify the mean. It's a very simple problem. So I will write again yt 1/3 yt minus 1 plus half yt minus 2 plus epsilon, right? Now to get a mean, I need to take expectation on the both the sides. So expectation of yt 1/3 expectation of yt minus 1 and half expectation of yt minus 2. My last term is actually 0, right? So if I actually write down, because this series has to be stationary, so it has to be mu, constant mu. So for all the expectation term, it has to be constant mu, right? Ups 1/3, this one 1/3 mu, and then I have to have a half of mu. But that is not possible, right? So only condition it is possible is if I have my mu equal to 0. So that's basically, since my series is stationary, so that's basically the answer. The mean of the AR2 series is basically 0, right? Great. So now the next question, I have to see if the value of rho 1 and rho 2. So let us write down rho 1 and rho 2. So of course, this is talking about the covariance of the AR2 series, and we will of course use the Yule-Walker equation. So remember the basic form of Yule-Walker equation. So this is basically gamma k phi 1 gamma k minus 1 plus phi 2 gamma k minus 2, right? So that's my Yule-Walker equation, and when k is not equal to 0. Remember this, because if you have k equal to 0, then you have a sigma squared term additional that will come. So so that is my Yule-Walker equation, and I can also write it in the form of rho. I can write rho k equal to phi 1 rho k minus 1 plus phi 2 rho k minus 2, right? Great. Now if I put k equal to 1, for k equal to 1, what I do is, so if I just substitute the value, rho 1 is equal to phi 1 rho 0 phi 2 rho 1, because I know here what I am doing is, I know that rho 1 is nothing but rho minus 1. We have explained that. Now my rho 0 is equal to 1, right? So that means I have phi 1 plus phi 2 row 1, right? And then it is very simple. I take row 1 this side, so it is basically phi 1 by 1 minus phi 2. So my phi 1 is equal to how much? 1/3. Phi 1 is 1/3, right? Phi 1 is 1/3. 1/3 by 1 minus half. So which means basically 1/3 half 2 by 3, right? So that is the value of my phi 1. Now I have to get the value of, sorry, that's my value of row 1, right? So now I have to get the value of row 2. So let me use a different color here, okay? So for k equal to 2, I get row 2. For k equal to 2, I will get in this equation row 2 is equal to phi 1 row 1 plus phi 2 row 0. Row 0 is equal to 1, right? So that means I can write equal to phi 1 row 1 plus row 2, and my value of my row 1 is equal to phi 1 into phi 1 1 minus phi 2 plus phi 2, right? So which would mean, let me do it here, or let me just minimize the size a little further, okay? So which would mean I have this is equal to phi 1 square minus phi 2 square plus phi 2 by 1 minus phi 2, which would mean phi 1 square means how much? Phi 1 was 1/3. So let me use another color, okay? Phi 1 square is 1 by 9. Phi 2 square is 1 by 4. And phi 2 is half. And phi 2 is half. So which means I will have this value equal to sorry, 36 4 minus 9 plus 18, right? Plus 18 by half. So which would mean 13 by 36, 13 by 36 into 2 by 1. So that means 13 by 18. So that's the value of row 2. Alright, so we get value of row 1, 2 by 3, and value of row 2, 13 by 18.